Okay, in this video, what I want to do is walk you through the process of converting a schematic diagram, like we talked about in class, to one that's more appropriately cast as an RTL diagram that you can use to write Verilog code to describe the circuit. Okay, so RTL, register transfer level diagram, is useful. It's what we do to help put circuits together. And in this particular circuit, there's some inputs labeled. You know, this is not a great resolution for the scan, but if you zoom in there, you probably see that's a B3, that's an A3, B2, A2, so forth. So it's defining bits, but it's not in the right notation for Verilog. The other thing to notice is that there's some full adders shown in the diagram, so I'll mark those off here. Here are the 4 full adders that we put together in a ripple style like we talked about in class. But the inputs for the full adders aren't shown, and we need to cast everything for outputs in Verilog notation as well. So S3, S2, those subscript notations, that's fine for representing a schematic diagram, but you want something that you can use to write Verilog code with. So what we're going to do in this video is walk through how you would convert this RTL diagram, this schematic, to an RTL. All right, so what I'm going to do first is I'm going to change this color scheme on my iPad to white, and I'm going to make the pen size a little bigger. And so my goal here is let's get rid of all the labels so we can redo our own. Okay, so we're getting rid of these. We're going to write over it and put our own labels on this circuit. Okay, so we don't need any of this stuff. We'll keep the outputs C and V. But there we go. So this would be a cleaner start for us. Okay, so let me also clean up the things I used to point. All right. And so this is a good starting point. And what we want to do is we want to simply label this with Verilog notation. Okay, so M is fine the way it is, because that can be a scalar. And M is that if M equals 1, we're doing minus. Okay, so just as a review, we have these exclusive ORs, and when we put the B variable into the exclusive OR, if you exclusive OR it with M, if M is equal to 1, it flips all the B bits. And then M is also a carry in, and so flip all the bits, carry in a 1, that's flipping all the bits, adding 1. So you're essentially doing addition with 2's complement, which is equivalent to subtraction. Okay, so that's the goal. All right, so let's go through here and let's label these in RTL notation. Okay, so these are the B's. Let me change that pen size. All right, so these are the B's. So this would be B3. This could be B2, B1, down to B0. Okay, and then we have A0 coming in, A1, A2, A3. So we didn't do much, but we recast this from subscripts to Verilog notation. Okay, the next thing that we need to do is do the same thing for the outputs S. So we have S3, S2, S1, and S0. Okay, so that's looking closer. But you notice we have full adders here, and there's not any inputs labeled on the interior of the diagram, so it's hard to know how things are supposed to be connected. All right, so let me give you a preview. We've written modules for the full adders, and you can tell right here, let me highlight this in yellow, the input names are X, Y, and Z, and the outputs are S and C. Okay, so let me go through the diagram and label those as well. Okay, so we have inputs X, Y, and Z, X, Y, and Z, X, Y, and Z, X, Y, and Z. So those are the inputs. Okay. we have the outputs S in this position, and then the C's, the carry outs, go to the carry ins of the next level. Okay, so the C's are here. Okay, so that's looking better. And the last thing we're going to need is we have full adders, but we need to instantiate them with a label. Each one needs a label because they're distinct circuits that show up in the Verilog implementation. And so when you initiate or instantiate a full adder, you have a label associated with it. So I've got these labels here. Let's go ahead and put those where they're consistent. So this is full adder 0, full adder 1, full adder 2, and full adder 3. Okay, so it didn't feel like we did a lot, and we in fact didn't do a lot, but we did something important. It lets us take a look at this schematic, and now it's an RTL diagram that we can use to write Verilog code. Okay, so for this lab, I've given you the top, all right? And so I told you, here's the inputs, A and B. Here's the input M. The output S is the sum output, and then we have some flag logic that you'll learn more about later, but you have an output C and an output V. Okay, along the way, I'm noticing that I connect these full adders together. And so how am I going to do that? And so it looks like I have some wires that I'm going to need to define. So I have right here a carry wire, CW1, that's carrying into the full adder 1. I have CW2 that's carrying into the carry input of the full adder 2, and CW3. I also have wires on the outputs of the exclusive ORs. Okay, so my notation for that was given by the wire command so I can be consistent. All right, so this would be BW3, BW2, BW. It's kind of hard to write in that small of a space, sorry. BW1 and BW0. So I have the wires coming out of the exclusive ORs also labeled. All right, so your job is to look at this RTL diagram and fill out the rest of the connections. Okay, so we've talked about how to do that several times. Okay, the first thing you're going to have to do is take care of the external circuitry. So we have some exclusive ORs here, 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 and here. So I get those started. B3, exclusive OR with M, connects to the wire, BW3. B2, exclusive OR with M, connects to the wire, BW2. So you finish that off, fill out the rest of those. All right, from there, you look, what's connected to the, excuse me, the X input. So go to the diagram. X is connected to BW0. All right, so you fill out the rest of this instantiation to get the Verilog description for the RTL diagram. Okay, so that's what you're going to be doing in this upcoming lab where we implement the add subcircuit.